Hi guys, welcome to lesson 20-3, starting on page 351 in your book. So this lesson is all about exponential decay. So we've spent some time learning the formula of an exponential function and studying growth factors and exponential growth. And naturally, not everything in the world grows exponentially, but things may also shrink exponentially, and that's called exponential decay. So we're going to be able to describe the characteristics of exponential decay functions, know what they look like, what the pieces mean, and we're going to graph and analyze some functions, and we're going to determine the decay factor of an exponential decay function. So a lot of this will kind of already make sense based on what you've been studying, and it'll just be the decay factor that'll be the new thing. So let's take a look. So before I just start doing this, there's a couple of things. These are always interesting to read. So you might already know this, but all radioactive elements have a half-life. That means they decay, and the half-life is the amount of time in which a radioactive element decays to half of its original quantity, its original mass. So interesting, those of you who, when I moved to Illinois, it's the first time I've ever had a basement. And when you have things that are underground, a lot of things come out of the ground like radon. And the U.S. Environmental Protection Agency, the EPA, recommends that the level of radon be below 4 picocuries per liter in any home. The EPA recommends that all homes be tested for radon. So I have a radon detector in my basement, and it was an alarming thing to think about radon leaking into my house. But anyway, I digress. So radon, a naturally occurring radioactive gas, was identified as a health hazard in some homes in the mid-1980s. Since radon is colorless and odorless, it's important to be aware of the concentration of the gas. Radon has a half-life of approximately 4 days. Tony's grandparents' house was discovered to have a radon concentration of 400. Renee, a chemist, isolated and eliminated the source of the gas. She then wanted to know the quantity of radon in the house in the days following. So that she could determine when the house would be safe. So first, what is the amount of the radon in the house 4 days after the source was eliminated? Explain your reasoning. So I think we'd say that there would be 200 picocuries per liter. Let's see, those look like PCI per liter. Because there were 400 to start with. And the half-life, and the half-life is 4 days. So since the source was eliminated, the amount left after 4 days would be half as much as it was before. So it has gone from 400 to 200. Then we're supposed to compute the difference in the amount from day 0 to day 4. So the difference is 200 picocuries per liter. And we're going to determine the ratio, so remember that's the fraction, of the amount of radon on day 4 to the amount on day 0. So on day 4 there's 200 to the amount on day 0, which was 400. So that would be 1/2. So we're going to complete the table for the radon concentration. So 0 half-lives, after 0 days, we started with 400. So 1 half-life, which is 4 days later, we'd have 200 left. The difference between these two is 200, but the ratio 200 to 400 is 1/2. And after the next half-life, which would be 8 days, it would be down to 100. So the difference would be 100, but the ratio 100 to 200 would still be 1/2. And then the next half-life, the third half-life, would be after 12 days. That would be down to 50. And the difference is 50, but the ratio 50 to 100 is still 1/2. So the the difference keeps decreasing. It gets smaller and smaller and smaller. It's not constant. You can see that the difference between consecutive days here goes from 200 to 100 to 50 to different half-lives. But the ratio is constant. So from one half-life to the next, the ratio is always 1/2, even though the difference from one half-life to the next in the concentration is getting smaller, smaller, smaller. All right, so we're going to graph the data from the table now. So on the first day, it started at 400. After one half-life, so these are the half-lives down here, not necessarily days. So after 4 days, which was one half-life, it would be down to 200. 2 half-lives, it would be down to 100. And 3 half-lives, it would be down to 50. And 4 half-lives, it would be down to like 25. That's not on there, but it would continue like that. So number 7 says the data that compares the number of half-lives and the concentration of radon are not linear. Explain why using the table and the graph. So not a constant rate of change. That's from the table. And then from the graph, that it's not a line. So graph is not a line. Can you tell I'm writing on a Mobi instead of my regular device today? Ew. Renee needs to know the concentration of radon in the house after 20 days. How many radon half-lives are in 20 days? Well, a half-life is 4 days, so that would be 5 half-lives in, I guess you'd say half-lives, wouldn't you? Half-lives in 20 days. And so that would be one more. We had already gone up to, well, let's see, we've gone up to 4, we got up to 3 half-lives. So we're going to go 2 more half-lives. So at 3 half-lives, it was down to 50, the concentration was. So then it would go to 25, and then it would go to 12.5. So 12.5 picocuries per liter. So then how many radon half-lives are in 22 days? And we're going to make a prediction. So 22 days are going to be, it's like another half of a half-life, right? So 5.5 half-lives. So if it's not going to quite get cut in half, but halfway, if we went to 24 days, it would be another half-life. So it would get cut down to 6.25. And because after 20 days, it was 12.5. So maybe halfway between there or so. Let's roughly say maybe around, I don't know, 8-ish. Approximately from 6 to 12, more like probably 9-ish picocuries per liter. Okay, so the decrease in radon concentration in Tony's grandparents' house is an example of exponential decay. Exponential decay can be modeled using an exponential function, which we've been using. The only difference is that in exponential decay, it's when the factor, the b value, in this exponential decay function, exponential function, it's when the b value is between 0 and 1. So remember, it can't be 0 because that would turn the whole thing into 0. And it can't be 1 because nothing would change if you just kept multiplying by 1. So if you multiply by something bigger than 1, then you're going to get exponential growth. And that's what we've been looking at. Now, if you multiply by something between 0 and 1, you're going to get exponential decay. Now remember, a b also can't be negative because that would cause it to jump back and forth. The function outputs would go positive, negative, positive, negative. And we know that on an exponential function, those outputs will never actually cross the x-axis, so they're going to stay above 0. So in a decay function, the value of b has to be between 0 and 1. So the decay factor in this case is 1/2 because we know it's dividing by 2 every time. And to divide by 2, we need to multiply by 1/2. So if we were going to write the exponential function for this data with 400 as the concentration that we started with, it would look like this. The function based on time would be 400 to start with times 1/2 every time that another half-life went by, another half-life time. So now we're going to use that function to think about the reasonable domain and range. So the domain in this story is time, right? So a reasonable domain would be time can't be negative, so the time has to be greater than or equal to 0. In fact, yeah, we really want time based on half-life periods. So to be specific, half-life periods. And we can have any amount technically. You know, it's not going to just jump from 4 days to 8 days to 12 days. There's going to be times in between. So anything greater than or equal to 0 would work. For the range, that's going to be our amount, our concentration remaining, so the radon remaining. And so remember, that one, it wouldn't go higher than 400 because that's where it started, but it could be equal to 400, so the radon has to be less than or equal to 400, and it'll never quite get to 0. So 0 would be less than the amount of radon, which would have to stay less than or equal to 400. So if we graph these, so we started with 400, and then after 4 days, we had well, or not. So let's talk about half-life period instead of days so we don't get confused. After one half-life period, we'd have 200, and after 2, we'd have 100, and then 50. So after 4 days, we only would have 25 left, and it would keep getting smaller and smaller and smaller. So that function would look like this, getting closer and closer and closer to 0. So you're probably already noticing from your experience writing functions, even from sequences, that original concentration, that 400, how it's related to the function and the graph. It's right there in the function. So it's the start amount, the start value in the function. It's also the A value, the letter A in the exponential function. On the graph, it's the y-intercept. It's where at 0 half-lives the amount we had. So it's the y-intercept on the graph, which is our starting place. Always has been. All right, so to use the function to identify the concentration of radon after 20 days, we're going to say, well, the radon based on time would be 400 times 1/2, and the number of half-lives in 20 days is going to be 5 because our half-life period is 4 days. So 20 days divided by 4 equals 5 half-lives. All right, so that's going to be our function. And then if we calculate that, we're going to get 400 times 1 to the 5th power is just 1, and 2 to the 5th power, let's see, 3rd power would be 8, 4th power would be 16, would be 32. So when we multiply this, we're going to get 400 over 32, or that's going to give us about 12.5. And this should match our prediction pretty closely. Matches our prediction. All right, so again, as always, I'm going to encourage you to try these yourself before you just copy what I say, because think about what is your power going to be when you try to do this one, when the time period's 22 days. So try it yourself, do some thinking and some struggling, see what you come up with. So let's see, our function is going to be radon based on time. It's going to be 400 for our starting amount times our growth factor of a half, and this is going to be a 5.5 for my half-lives. If I've got 22 days and my half-life period is 4 days, then this is going to give me 5.5, or about 5.5 half-lives. So when I calculate this up, I should get 1 over 2 to the 5.5 power is going to be something about, now we're getting approximate now because I'm rounding, 45.25. So then when I multiply this, I'll get 400 over 45.25, or approximately, I'm going to come out with, let's see, I'm going to do this in my calculator. I'm getting about 8.84, and that's close to our 9 prediction. Pretty close. Now we're more precise than we would be just predicting off a graph. Now, this is a great question. I want you to really think about this. Will the concentration of radon ever be 0? Explain your reasoning. So pause and think. Pause me and think. So no. The values keep getting tinier and tinier, but they'll never reach 0. But they'll never actually disappear. That's because there's an infinite number of numbers, even between 1 and 0. They'll just keep getting tinier and tinier, smaller and smaller and smaller decimal. Never actually reach 0. And that'll be fun when you get to calculus. You get to discover what happens when functions approach 0. That's basically limit theory, and that'll be fun for you. So sorry for the messy writing on this one, but bring any questions you've got. Be real clear about all the different components, and we'll pick it up together in class. See you there.